Hi everybody, I'm going to introduce to you the height of the ceiling lab, walk you through the theory behind it, and then what you're going to eventually have to do either through watching the videos or the clips that follow this video, then do the calculations on your own and draw a conclusion, and hopefully come up with a result that you're satisfied with. There are a number of goals in this lab. Not only to the main goal, main purpose is to find the height of the ceiling of this room without measuring it directly. All right, so if I were to give you a meter stick or a ruler or any other length measuring device, you could come up with some method to find that, and that's important. We're going to do something a little bit more sophisticated, and in the process learn how to make other measurements that are important in this class, and then put them together using some physics you haven't learned. Eventually you'll learn, but you don't have to know that for now. Put those measurements together in an equation, and from that equation we can say the height of the ceiling must be this. And that's a very powerful technique. I alluded to that and gave a little video on that when we were talking about figure out the mass of the Earth or the Moon. You can measure an object orbiting that, namely its period and its distance, and from that and your knowledge of gravity, you can put together an equation that ties together distance, period, mass, and the force of gravity. And that's how we determine masses in astronomy. Okay, so in order to figure out what we have to measure to allow us to calculate the height, we want to look at the actual physical phenomenon. So we have an object that's freely falling through the air, and we can ask ourselves, how much time does it take to hit the ground? Or what factors affect how much time it takes it to ground? In other words, if I want it to fall for a long time, what would I change about the situation? Or if I want it to fall a short time, what would I change? So I want you to pause right here, brainstorm, and write down as many factors, things that you can measure that would affect it. And then I'll go through and tell you which ones we're going to use for this lab. If you're wrong in your brainstorming, it's not a big deal. It's a brainstorm. You're allowed to be wrong, but I want you to start thinking what makes sense to you. So again, pause. Once you've written things down, start this again. Okay, so it turns out that there are three factors that we're going to test. There's a fourth factor you might have put there that we're going to try to eliminate because it complicates things a lot. So to me, the most obvious factor that determines how much time it takes for something to fall is the height that it falls. All right, a distance, and we're going to call that h. So a large height takes a long time, a smaller height takes less time. Secondly, you might have thought, maybe didn't, that the object itself or something about the object itself affects its fall, and you might have thought that its mass might matter. Okay, we're going to call mass m. So that's another thing we're going to build into our calculation that relates height to time, or time to height. Now, related to mass, but not the same thing as mass, even though they're often interchanged, is the force of gravity. So you maybe put something about the pull of gravity. You might have written the word gravity. I'm going to use a substitute word, and that's called weight. Okay, we'll eventually learn, we don't have to know that for now, that weight is not the same as mass, and it's associated with gravity, and we're going to call that W. So those are the three factors we're going to test to figure out the time, take that back, let me be clear. These are the three factors that affect time in the air. And we see that time in the air is related to height. And the goal of our lab is to find height, so if we turn that around, we can use time in the air to find height. The fourth thing that I mentioned that we're not going to test is the medium through which it falls. In other words, in this case, the object is going to fall through the air. That air is the medium. You could measure medium as density. You could have a fall through water, and we know as it falls through water, the time is going to be very different than it falls through air. But how to translate that into an equation is complicated, so we're going to basically take out the effects of air by doing three things. Drop it over a short distance. Ceiling to floor is not a very long distance. Drop a compact object, in other words, we're going to drop a ball, and make sure that object is fairly massive, so it's not going to be a tiny little sphere, it's going to be a lacrosse ball. By doing that, the effects of air are basically minimized. Okay, so we have 4 variables: height, mass, weight, and time. And so there's an equation that relates all those for a free fall event, which is what we're going to be doing. You don't have to derive that. I'm just going to give that to you. Eventually, we will learn that. So the equation that I'm going to give you is this, that the square of the time, okay, is equal to, parentheses, twice the mass of the object times the height that it falls, all divided by the weight of the object. And I've written here what each of those variables stand for so you don't forget. So what we're basically going to do in the procedure and materials that follow is you're going to measure this for a ball dropping, you're going to measure the lacrosse ball's mass, and you're going to measure the lacrosse ball's weight. Well, if you're remote, you're not going to measure directly, but I'm going to have video that you can take measurements based on what you see on the video. If you have those three, then you can solve this equation algebraically to get the height of the room. And that's what we want you to understand. So the success for finding the height of the room depends on two things: your ability to rearrange this equation and solve it algebraically, and more importantly, and one of the key objectives of this lab, is to measure these accurately. Okay, so we're getting some measurement skills in there. As I alluded to, we're going to follow these these procedures, and those who are watching the video clips this is what we're doing for you. You're going to record all your data right here. I've set up a data table for 10 trials of the dropping of the ball. So you're going to record each one. Notice I've put the units in a table, so you don't have to write seconds every time in each box. And then once you have those 10 trials, and they should not all be the same numbers. As I'll show you in the clip that after this, you're going to have to get a stopwatch out and measure each of those times for each of the clips. And you're going to want to come up with a process that gives you something that's accurate. Anyway, once you have those 10 measurements, you're going to take an average. You're going to mass the ball in grams, convert it to kilograms, and then you're going to see a video clip where you get the weight of the ball. Once you have those three measurements, you're going to take the equation from the front, show me some algebra such that you work it out yourself, maybe do it on paper and then transcribe here, and then you're going to come up with an equation that solves in terms of h. So right now we have an equation that's solved in terms of time, so I want you to basically rearrange this so h equals some combination of those other factors. Once you have that equation, you're going to plug in your values from up in your data table, and you're going to show me your substitution of units here, and then give me a final result there. But hopefully you get a result that makes sense. In other words, you should have a rough idea of what the height of the ceiling of this room is in meters. So if you come up with an answer in your calculator of 0.1 meters, that's wrong. Either you solved your equation wrong, or you plugged in the wrong numbers, or you pressed the wrong buttons on your calculator. If you get 15 meters, that's way too big. Okay, so your answer should make sense. Once you come up with an answer, then the third page, you have a conclusion, and I want you to do some analysis on the quality of results and then what measurements might have been not as accurate as you wanted and what you could do and improve. Good luck. Take your time with this, especially with the timing part. Okay, so the first measurements that we're going to do is we're going to drop a ball from the ceiling, let it hit the floor, and you're going to time it. You're going to need a stopwatch to do this. It can be from your phone or any other device that can measure out to the hundredths of a second. Timing, so there'll be 10 trials of this. Timing is not an easy thing to do, so work out a method. It might take you a few attempts to do this properly, but accuracy is important, as is precision. Precision is consistency. You don't want to be all over the place because it's a fairly quick event, and you certainly want to be accurate. You won't have any way of knowing how accurate you are until you get your results, and that's something I'll talk about eventually in class. So when you eventually put your times together and the other measurements, the other two measurements on the subsequent videos will be the mass of the ball and the weight. You will find that if your calculated value for the height of the ceiling is off from the measured height, you want to pinpoint where that comes from. And I'll let you discuss that, but we'll eventually talk about that in class. So good luck. 2, 3, drop. 3, drop. 1, 2,
3, drop. 2, 3, drop. 2, 3, drop. 2, 3, drop. 2, 3, drop. 2, 3, drop. 2, 3, drop. 2, 3, drop.
All right, the first thing we're going to do is calibrate the spring scale so it starts at 0 newtons. Go ahead, Mr. Sedita, why don't you go ahead and tighten that up to lift up the measurement mark. Keep going. You're at 0.2 now. 1.5, 0.1 and 0.5, 0.1. Keep going 2 more twists. I think that's good right there. All right, so at this point, if we put the lacrosse ball in a nearly massless plastic bag and hang it down, we can get that. And let's go ahead and reach in and get a better scale look at it.
So this is our weight of the lacrosse ball, and the units which say N on the scale is newtons. We'll learn about that later on, but for right now the unit of weight is a newton. All right, so the last thing we're going to measure is the mass of this. Now the scale will do it in grams. Eventually, you're going to record it in grams, but you're going to eventually convert to kilograms to do the calculation.
We're going to expand that.
Okay, so record that value, convert, and you should be good to go.